Good morning, everyone, and welcome to another live Quantzer user webinar. In this webinar series, we highlight the work of academics around the world that use Quantzer solutions and technologies. My name is Michel Levy, and together with my colleague Gemma Wang, we will be your hosts and moderators this morning. Today, we are very excited to have Dr. Kumar from the Vellore Institute of Technology in India, or VIT. Dr. Kumar will show how he and his team have been using iterative learning control, or ILC, and reinforcement learning techniques to do reference tracking and vibration suppression on our Quantzer rotary flexible link system. And on that note, I'd like to hand it off to Dr. Kumar, and thank you everybody for attending.
Thank you, Miss, for the nice introduction and sharing the way we can go about for the seminar. So thank you, Gemma, for coordinating. Let me confirm whether my screen is visible. Mick, is my screen visible?
We can see your screen, Dr. Kumar.
Thank you, Gemma. Okay. First of all, I would like to thank Quantzer for this opportunity to take part in this webinar. And I'm Vinod, professor with School of Electrical Engineering in VIT Vellore. And today I'm going to talk about the learning control schemes for under-actuated systems. The presentation is actually planned based on this aspects. So this is the outline of my presentation. So initially, I will talk about the limitations of feedback control and what is the motivation for going to learning control. And I will also touch upon what is under-actuated systems and what are the typical under-actuated systems from Quantzer that we use in our laboratory. And later, I will talk about a class of iterative learning control and their implementation for a couple of systems, namely maglev system and ball balancer. And the second part of this presentation would also touch upon the implementation aspects of deep reinforcement learning control for a rotary flexible link system. And finally, I will just discuss what are the real-time challenges that we have faced while implementing this DRL on a RFL system. With that, let me get started. So I just would like to motivate the need for the learning control scheme through the celebrated board sensitivity integral problem, or also called waterbed effect. In fact, to understand the waterbed effect, let's make use of this simple block diagram representation of a feedback control scheme. So what we see here is a typical feedback control scheme, which contains the standard notation such as P of S represents the plant, C of S is a controller, R is a reference input, and Y is the measured output, D is the external disturbance, and N is the sensor noise. So if we apply a simple superposition principle and come up with the transfer function among the external variables, such as the 1 to the reference, 1 to the disturbance, and the 1 to the sensor noise, we could arrive at the expression for the output being this expression. So in which we can notice a couple of factors called a sensitivity function and the complementary sensitivity function. Typically, the goal of a feedback control can be stabilizing an unstable system into a stable one, which can not only track the reference input, but also reject the external disturbances and also attenuate the effect of the sensor noise. Hence, if we design a control in such a way that if we have this sensitivity function and the complementary sensitivity function being small, then we would be able to achieve the required objectives. But unfortunately, there is a constraint on that. So when we sum up this sensitivity and complementary sensitivity function for a CISO system, typically it would be is equivalent to 1. And of course, it's for a MIMO system, it's equivalent to a identity matrix. So what it says is that the sensitivity function and the complementary sensitivity function cannot be small in the given region. For example, if you are trying to make the sensitivity function small in the low frequency region, we'll have to compensate the fact that it will be high at the high frequency region. Of course, we can ask ourselves this question, like, what are the benefits that we get? When the sensitivity function is small, we would be able to achieve the low tracking error. And when the complementary sensitivity function is small, we will be able to have excellent noise rejection characteristics. So this is known as the Bode sensitivity integral or waterbed effect. So it is not possible to make this S and T small at same frequency. So point is, we would like to make this sensitivity function small at a low frequency region and this T to be small at high frequency region, so that we will be able to have a trade-off between the reference tracking and the disturbance rejection feature, which could be easily identified through this example sensitivity and complementary sensitivity function plots. So you can notice that typically the sensitivity function would be small at the low frequency region, and it would be high. Of course, if you are making that small at the low frequency region, you will have to compensate the fact that it is high in the high frequency region. So typically, for good noise rejection features, we would like to have the complementary sensitivity function being small at the high frequency region. Hence, the typical LTI system have this constraint of waterbed effect. So the question is, can we improve the performance of a feedback control by incorporating the concept of learning into the framework of a control scheme? So that motivated us to turn to this intelligent approach called learning control scheme. Of course, there is one more motivation which we can say. Most of the model-based approaches require the exact plant model. But when we go for the either first principles model or the physics-based model, it is not possible to accurately model the dynamics of a system. There will always be some neglected dynamics, which may result in poor control performance. So is it possible to have a control framework which can compensate this aspect? Of course, the answer is yes, through this learning control scheme. And this learning control scheme draws inspiration from the way human learns things. One simple analogy that we can relate here is that assume that a person is trying to learn the skill of playing a basketball. So if he is attempting a free throw from a fixed position, by observing the trajectory of the ball over the subsequent trials, he or she would be able to acquire the skill of playing the game in an effective way. So what is the underlying principle here is that experience, or based on the trial and error approach, he is actually trying to correct his motion in such a way that the goal in this case can be achieved. So now the point is it possible to incorporate that kind of learning or kind of an adaptation to the control framework in order to improve the performance? Yes, so that motivated people to turn to this learning control. And this learning control scheme is an iterative approach which is used to improve the quality of the performance for the system that perform the task in a repetitive way. So another major reason for this learning control is that most of the non-learning control schemes, such as PID, continue to result in same tracking error in every trial. Or we can also put it like this, that the PID controller fails to capitalize the information-rich tracking error signal. So way back in 1984, a group of researchers from Japan asked this question, that is it possible to improve the performance of a repetitive system by learning the dynamics of the system through the error sequence? Of course, the team led by Arimoto came up with an answer that yes, it is possible, and they formulated the basics of this iterative learning control. So in short, making use of the error signals and the control sequence that was supplied to the system in the previous iteration, the iterative learning control aims to improve the performance of a repetitive system iteratively. So that's the basis. And it's actually a kind of a feed-forward control scheme. Um, the ILC is a kind of a feed-forward control scheme, which would be added on top of the existing feedback control structure. So we can view something like this. In most of the applications, we may not have the privilege to altogether replace the existing feedback controller to improve the performance. Is it possible to improve the performance, say, by augmenting another control scheme in the form of a feedback structure? Yes, it is through this ILC. So as mentioned, this ILC is initially proposed for a repetitive system. So what is meant by a repetitive system? The system which performs the task over and over again. For instance, in the case of a robotic manipulator, say if it is used for material transfer application, say moving an object from one location to the other location. Then if the robot is going to perform the same operation over and over again, then it would continue to result in same tracking error in the case of a non-learning controllers. Whereas what this ILC aims to do is that it aims to capitalize on the error signal and the control signal supplied in the past iterations so that it could come up with new set of control sequence that could improve the performance of the repetitive system iteratively. And of course, it comes with certain assumptions or restrictions. So one of the assumptions in the ILC design is that the system is invariant under repetitions. That is, the system returns to the same initial condition in every trial. And it also assumes that the system is stabilized with the help of a simple feedback scheme. So this is one block diagram explaining the standard ILC scheme. You can see it is a kind of a memory-based, control architecture. So it records the control signals supplied. So first of all, let us take a look at this variables involved in the structure. Here, UK of t indicates the control sequence and YK of t is the measured output, YD is the reference signal, and UK plus 1 of t is the next control sequence. Basically, making use of the control signal supplied in the previous iteration and the tracking error, the iterative learning controller produces the supplementary control action in such a way that it can iteratively minimize the tracking error. So the goal of this ILC is to design the control sequence U of k plus 1 by making use of the previous information. So what do we mean by previous information here is that by utilizing the previous control signal supplied to the plant and the tracking error. And making use of that, here the goal is to ensure iteratively make the output to follow the desired trajectory. Hence, the standard ILC algorithm put forward in the beginning was actually making use of the control sequence and the tracking error. So this gamma indicates the learning rate. So particularly here, I'm going to touch upon a class of ILC called current cycle feedback ILC. So this block diagram shows a combination of a feedback control and a feed forward control in the form of an ILC. So what this C indicates is that it's a feedback controller. And what you see everything at the top represents the iterative learning controller. So it's a kind of a add-on scheme. That's what we mentioned. So one of the assumptions is that the plant is stabilized with the help of a feedback controller. And here the goal is to design the couple of filters such as the learning filter and the roll-off filter. The learning filter receives the tracking error as an input and produces the subsequent control action. And the role of this purpose of this Q filter is to ensure that the high frequency dynamics are removed. So this will typically be a low pass filter. And in terms of the parameters, when we notice here, you can notice that the input to this summer is one is from the feedback controller and another one is from the iterative learning controller. So the feedback control is augmented with the control signal from the iterative learning control. So the augmented control is given to the plant in such a way that iteratively this can make Y to reach R. Hence, from the block diagram representation, we can write the learning rule U of k plus 1, that is the control sequence at the next iteration or the next trial would be, we can easily follow that it is going to be C times E of k plus 1, which is from the feedback controller, and L times Ek, which is from this learning filter, and Q times UK, where UK is the control signal supplied in the previous iteration. And we can easily write the expression for the error in the next iteration, which is R minus Y of k plus 1. So if you replace this factor E of k plus 1 by R minus Y of k plus 1 and rearrange and do a little bit of manipulation here, you could come up with the expression something like this. Likewise, we can also write an expression for the error for the current iteration, which is R minus P times UK. We can easily find out that expression. Notice this EK would be R minus P times UK. And then we can replace this factor EK with this expression and do as a manipulation in such a way that you segregate the like terms together. So take this U of k plus 1 term to the other side and combine the terms of UK and separate that into the control signal and the reference input. And then if you take this factor to the other side, we can come up with the expression for the control signal for the next iteration. For this control sequence to converge, we need to design the factor learning factor row in such a way that the norm of the difference between the control sequences monotonically decreasing. Hence, from the previous expression, if we select this factor which is associated with the control signal to be much lesser than 1, we would be able to achieve that. And ideally, if we select this factor Q minus LP to 0, it ensures the convergence. So from this, we can find out the expression for the learning filter L. So it would be given by P inverse times Q. So the learning filter can be determined by making use of the inverse of the plant model multiplied with the roll-off filter. In order to guarantee the robustness, typically the Q filter is chosen to be a low pass filter. Hence, combining this, the updated control law for this ILC can be written as it is L times EK plus Q times UK. So the design of this ILC is all about, the selection of this L and Q filters. So the Q filter is typically chosen to be a low pass filter and L is determined based on the plant inversion technique. And I'm going to explain how we applied this for a couple of under-actuated systems that we used from Quansa. So before I talk about it, I just would like to motivate what is under-actuated system. Typically, the under-actuated systems have fewer number of actuators than the degrees of freedom to be controlled. And what is the reason for introducing this under actuation? Of course, there are many reasons. One is, say, we would like to reduce the weight of the system or the cost and energy, and also tolerance for the failures. We also would like to ensure that the same amount of dexterity is maintained even if it is an under actuated system. So one challenge that we have here is that unlike a fully actuated system, which have same number of actuators as the degrees of freedom, with fewer number of actuators, we are trying to have same dexterity, so the control becomes a little more challenging. So this under-actuated systems are predominantly used in several applications, such as mobile robots, spacecraft, and locomotive systems. Coming to the academic environment and the kind of experimentation that we do, in the laboratory system, we do have a couple of systems such as magnetic levitation system and ball and beam system or ball balancer. So I'm going to now explain how this iterative learning control is extended for a magnetic levitation system to realize the precise tracking of the ball. So this shows the Quanser magnetic levitation plant. So the basic idea is we know that the magnetic levitation contains the electromagnet at the top, photosensory circuit at the bottom. The objective is to make the steel ball levitate by controlling the current given to the electromagnet. According to the amount of current given, it generates an attractive force. The point at which this attractive force is equal to gravity force will make the ball levitate. So by controlling the coil current, we would like to control what is the position of the ball. So in order to do this, first of all, of course, we identified the dynamics of a system, or I would say like we went for the first principle model to understand the need for a controller. Before that, what you see on the screen is the standard, parameters of the maglev system. And typically, if we see the first principle model of this magnetic levitation system by accounting all the forces acting on the ball, the total force acting on the ball is a combination of a gravity force and the attractive force created by the electromagnet. And it's actually a second degree equation and taking a Laplace transform and then finding the ratio of the ball position to the coil current gives this transfer function. So what it basically conveys is that we can notice from the denominator polynomial that it has the unstable poles. So the one pole is on the left half of the plane and another one is on the right half of the plane. So that motivates us to go for a feedback controller. So it is important to mention that here in our work, we actually had a goal of improving the trajectory tracking performance of a magnetic levitation system. So to achieve that goal, we augmented the standard PIV control scheme with the iterative learning control scheme. What you see here in the dashed line is the standard PIV control scheme, and the one that is shown in red dashed line is the iterative learning control scheme. So the control input to the plant is a combination of the control signal generated by the PIV and the control signal generated by the iterative learning control. So as mentioned, the plant is unstable in open loop. Hence, to stabilize that, the PIV controller is utilized. And the goal of this iterative learning control is to make use of the information rich error signal and come up with the control sequence that would iteratively minimize the tracking error. So in short, this would take care of the stabilization process, and this would ensure that the tracking error is iteratively minimized. And we would also show the performance of a system which has only PIV controller and the system that has a combination of PIV and the iterative learning control. So before that, these are some of the standard parameters that we have used for the feedback controller PIV based on the pole placement technique. And according to the dynamics of the magnetic levitation system, the role of filter is chosen to be chosen to have a low pass filter characteristics. And then the learning filter L is determined based on the plant inversion technique. And this is how the experimental setup is. So typically by controlling the coil current, we control the ball position. So through the DAC, the control algorithm implemented in the PC is interfaced with the signal conditioning circuit, that is the power amplifier. So which in turn, supplies a coil current to the magnetic levitation plant, and through the photosensory circuit, we measure the ball position, and that is taken for the feedback. Okay, so this is the tracking results of the only feedback control scheme and the combination of feedback and ILC. So what you see on the left panel is the response of the PIV controller alone, and what you see on the right hand side is the response of PIV augmented with iterative learning control. Of course, for both the control scheme, same reference signal is supplied, and we can notice from the response plot that unlike a PIV controller, the augmented ILC yields precise, of course, better tracking in terms of the ball position. So the tracking error in this case is, less compared to the response of a PIV controller. And in order to analyze the performance, this plot shows the CPSD of the tracking error. CPSD stands for cumulative power spectral density. We can notice from the CPSD plot that in the high frequency region, the performance of ILC is significantly better than the performance of the PIV controller. So by augmenting ILC, we can achieve the reduced vibration around the steady state and also can improve the high frequency tracking performance. So this is one such system that we have tested the response of an ILC. And of course, this shows the amount of control effort supplied to the electromagnet, that is the coil current. So this is for the PIV and this is for the augmented one. And finally, to assess the robustness of the control schemes, both the control schemes have been supplied with some external disturbances and the responses were recorded. So what you see on the left-hand side is the response of only PIV. You can notice that the magnitude or the deviation of the measured output and the time taken to come back to the reference tracking is significantly large in the case of only PIV compared to the PIV ILC. So I just would like to show play one simple video that we have actually recorded while conducting this experiment. So just a minute. Yeah, so this is the magnetic levitation plant, and of course the control algorithm is implemented in Simulink, and for interface we use a Quark. And what you see on the screen is the experimental demonstration of this ILC PIV scheme. So in the interest of time, I just would like to directly go to the combination. So I just put this stop here. So you can notice what you see here is actually the plant model. And what you see here is a typical PIV controller where I am actually moving my mouse. And what you see here is actually the learning filter and the roll-off filter, which is going to supply the additional control effort to ensure that the tracking error is minimized. So I just would like to play this and show the response of a system. So typically, two-channel DAC is used for measuring the signals. Yeah, so this is the response of only PIV controller. You can notice that the ball is getting levitated, and you can notice that the response is a little oscillatory around the reference trajectory. Now this is the response of the augmented PIV and ILC. So compared to the previous case, when we test this on a real-time setup, we could see that the deviation has significantly reduced. And what you see here is the response of a system when it has some external disturbance. All right. Okay, so the second system that we attempted was the ball balancer. In fact, this schematic diagram conveys the overall idea of the scheme. Typically, by taking the visual feedback of the plate, we actually come up with what should be the corresponding servo angles that can maintain this plate to be a stable one, so that the ball can move according to the user trajectory. So in this case, as this is a cascade control scheme, we augmented the ILC and the outer loop. You can notice the inner loop is actually a servo for controlling the servo angle, and the outer loop is used for controlling the ball position. So the feedback controller is augmented with the iterative learning controller in order to ensure that the tracking error is minimized. So for which the response that we recorded in the form of a phase plot is shown here. The one on the left is the response of a PV controller. The red line indicates the reference trajectory, and the blue line indicates the actual response of a PV control alone. Whereas on the right hand side, it is the black dashed line indicates the response of a PV ILC scheme. So I just would like to play another video which shows the different test cases that we attempted for this visual servo system. So this is the experimental setup with data acquisition board, signal conditioning circuit, and the ball balancer unit. So 3 different test cases we attempted. And what we are going to see now is the combination of PV and ILC, that is proportional velocity controller augmented with iterative learning control. And this shows the Simulink model. So the first test case that we attempted was the a robustness assessment. Like the goal here is to check how closely the ball is able to track the reference trajectory, even if the lighting conditions around the system is poor. So in fact, deliberately the lighting conditions around system is made poor, and the response of PV and ILC are tested. Similar way, the second one is the stabilization characteristics of the control scheme when it has a stochastic initial condition. So when the ball is thrown from different positions at a control speed, whether it is able to stabilize it on the plate or not. And the third test case was, when it has a time varying set point profile. For example, the reference profile given generated is something like this, which has abrupt change in the magnitude and also in the direction. And we did test how closely it is able to track, and we could notice that the response of ILC was better than the response of a PV control. So in short, augmenting learning scheme with the feedback controller for a repetitive system can improve the tracking performance significantly. All right. So that takes us to the end of the first part. And now I also would like to briefly touch upon the another learning control scheme called reinforcement learning control that we implemented for a rotary flexible link system. We know the reinforcement learning is a kind of a machine learning algorithm. This reinforcement learning is a model-free framework which contains the two basic entities such as agent and an environment. Here, the agent takes an action and observes the state information. And according to the action it has taken, it is going to receive some reward. The overall goal of the reinforcement learning control is to maximize the reward that the agent receives. So it's a kind of a goal-oriented computational paradigm. So it aims to train the agent in an unknown environment so that without any supervision, the agent can acquire the knowledge or ability of achieving the goal through interaction. Particularly, I just would like to touch upon the standard, the oral framework. That's the one from MathWorks even. So what you see here is the agent, which contains the the policy. So the overall goal is to identify or come up with an optimal policy in such a way that the control goals are met. So here the agent takes an action. Anything outside the agent is viewed as an environment. And when it takes an action, it observes a state. And based on the actions taken, the agent would receive the reward. And based on the reward, the learning algorithm would decide how good the actions are. Accordingly, it is going to update the policy, and iteratively, this is going to improve the performance. And as it is based on the trial and error, of course, the training reinforcement learning agent is an important aspect in the case of a control implementation. And what we see here is the standard comparison between the conventional control systems and the reinforcement learning framework. Probably in the interest of time, I just would like to move on to the implementation of one kind of oral framework that we attempted. So typically, the oral workflow contains 7 different tasks. One is to formulate the problem, that is the kind of problem that we are trying to address. And then we need to create an environment. Anything outside the agent is viewed as an environment in the case of an oral framework. And we need to identify what is the reward function. So typically here, when we say a reward function, it could be mapped to the corresponding or cost function in the case of a conventional feedback control. And then we need to create an agent and train the agent in an external environment and assess the performance of the agent or validate the agent. And if it has been trained, then the trained agent can be deployed in the form of a policy. So this shows the different classes of deep reinforcement learning algorithm. Typically, they are of 2 types. One is a model based, another one is model free. Particularly, again in model free, there are 2 branches of oral framework. One is value based, another one is policy based. The one that we attempted is a deep deterministic policy gradient algorithm, which is based on actor critic method, which actually combines a value based and policy based methods. So the deep deterministic policy gradient is a model-free off-policy actor-critic network. It basically contains a couple of networks. One is a main network and another one is a critic network. The role of a main network is to generate the action and learn from the states. And the purpose of the critic network is to assess how good the actions are. In order to achieve this, it also contains two more networks, such as online networks and the target networks. The basic idea of introducing the target network in the DDPG framework is that in order to ensure the stability of the convergence. For example, instead of directly updating the main network during the training, initially the target networks are updated, and based on the response or the um, Q value, the online networks are updated. And what you see here is the DDPG framework for the RFL system. So as you can see, it contains the main network and the target network. So this is the main actor network and this is the main critic network. The main actor network is going to generate the action, which is actually augmented with a noise model so that the algorithm will have the exploration capability. And for the action taken by the agent, the actor network would also receive the states. And this is information is used, such as the action taken by the network and the states are used in the critic network to assess how good the actions are, whether it is driving the system towards its goal or not. Accordingly, the parameters of the actor network are updated. And this process is continued until the specified number of episodes. So this shows the pseudocode of a standard DDPG algorithm. Initially, we set the critic network and the actor network and take a copy of the networks such as the target and the main networks. And then we use a concept called replay buffer here so that we would actually take a mini sample of the transitions available in the network for training the agent. So first, the actor network is going to perform an action. For the action it has performed, it's going to receive the reward, and it is going to observe the states. Based on the measured states and reward, it is going to compute what is going to be the Q value, and through that it is going to minimize the loss function by means of a temporal difference error. So this loss function would be obtained by minimizing the error based on the temporal difference. And then the gradient ascent approach is used to update the policy network so that this process is repeated until the network has received the maximum reward. And finally, in order to ensure the stability of convergence, soft target update is followed so that the target network is updated initially, and then based on the performance, the main network is updated later. So in short, we can view like this. So the DDPG framework contains a couple of networks. One is actor, another one is critic. The role of the actor is to take an action, and the role of the critic network is to evaluate how good the action is. According to the performance, the critic network is going to update the parameters of this actor network. And this is actually implemented for a simple rotary flexible link system. We know that the rotary flexible link system contains a servo motor. On the shaft of the servo motor, external flexible link is attached. Now the control goal is to make sure that the servo follows a reference trajectory. While doing so, we should ensure that the vibration at the tip is as minimum as possible. So this is one system which emulates the control challenges that are encountered in the light space structures such as robots and spacecraft. So from control standpoint, we can say that the manipulated variable in this case is control motor voltage, and the controlled variable are servo angle and the deflection angle. And this shows the standard RFL plant parameters. As the The RFL is unstable in open loop. In order to identify the mathematical model, we went for the closed loop identification technique. Of course, there is another reason. We also would like to compare the performance of DRL with the standard model predictive control. So as the model predictive control it requires the plant model, in order to identify that, we went for the closed loop identification technique, in which we followed the direct approach. We can notice that the model predictive controller is implemented and the input and output variables are recorded. The input variable in this case is the motor voltage, and the output variable is the servo angle. So firstly, the input and output data are recorded, and then the power spectral plot of the RFL system is obtained. So this shows the power spectral plot. From this, we can notice that the RFL exhibits low pass filter characteristics. Hence, we actually perform the model validation by means of three standard tests, such as deterministic test, stochastic test, and the correlation test. So what we see here is the correlation plot for the input lags and the correlation of the residuals. So we can notice from the top plot that none of the residuals is beyond the threshold. This indicates that this has managed to capture the deterministic part of the system effectively. Similarly, to test how effectively it is able to capture the stochastic part of the RFL system, the autocorrelation function is shown here. We can notice that except the zeroth lag, none of the residuals is beyond the threshold. And finally, the model is fit by dividing the data samples into 80% for training and 20% for testing. We can notice that the test model is able to predict the dynamics of the system. And so we built a ops model, auto regressive model, and this shows the ops model built based on the system identification technique. And for comparison, we went for an MPC. So typically the MPC, we used the sampling time of 2 milliseconds and the prediction horizon of 132 steps and the control horizon of 2 steps. It is important to mention that the system should respect the hard and soft constraints. The hard constraint here is the motor voltage. It should ensure that the motor voltage does not cross 10 volt. And the soft constraint is the deflection angle, which should guarantee that the deflection angle is well within 5 degrees. And this is the configuration parameter for the deep reinforcement learning. So the sampling time is again 2 milliseconds in this case, and it is trained for a maximum episode of 1000. And the learning rates of the actor and critic network are chosen to be 10 to the power -4 and -3 respectively. And this shows a simulating diagram of DRL for the RFL system. You can notice this is the RL subsystem, and this is the RFL system. And this shows the physical connection of the experimental setup. So basically, the rotary flexible link contains a couple of sensors, optical encoder and a strain gauge. Optical encoder is to measure the servo angle. Strain gauge is to measure the deflection angle. So the controlled variable in this case is VM. And this shows the tracking performance of the reinforcement learning controller and the model predictive controller. So what we see here in the green is the reference or the command, and the dashed blue line is the response of a model predictive control, and the dashed red one is the response of a reinforcement learning control. So from the response, we can clearly notice that the reinforcement learning controller is better than the response of a model predictive controller in terms of the servo tracking. Similarly, the interesting aspect is that the vibration suppression feature of RLC is found to be way better than the suppression feature of MPC. You can notice the one that is shown in blue is the response of MPC and the one in red is the response of RLC. So the RLC is able to significantly minimize the vibration at the tip. And this shows the amount of control efforts applied to the system. And the hard constraint that we had was it should be restricted within plus or minus 10 volt. And we can notice that, the hard constraints are respected and the control voltage in the case of RLC is plus or minus 1 volt, whereas in the case of MPC is plus or minus 2 volt. Finally, for assessing the robustness, the external disturbance is injected in the form of a pulse signal into the system. And you can notice the response of MPC and RLC in this plot. Notice the deviation in the case of an MPC is significantly high, whereas the RLC is able to regulate the servo wave close to the reference trajectory. And this shows the zoomed in view of the same plot, particularly during this region. And this is the response of deflection angle. We can notice that the deviation in the case of RLC is much less compared to the MPC. So the similar one is tested for the continuous disturbance also. So as it is similar, I just would like to wrap up this presentation by playing another video that shows the demonstration of this RFL. Yes, so this is the real-time testing of the DDPG framework for the RFL system. So what you see here in the insert image is the movement of the RFL system and the implementation in Simulink. So we can see the three different plots. The left one is the deflection angle alpha, and the middle one is the servo angle theta, and the third one is the control input voltage. So we can notice the movement of the flexible link for DRL is pretty close. You can also notice that the vibration at the tip is much less. In fact, it's close to plus or minus 1 degree, and it is able to offer precise tracking. So this is the response of deflection angle. You can notice that it is regulated well within plus or minus 1 degree. That is evident from this video that it shows the flexible link movement. All right, in the interest of time, I just would like to wrap up this presentation by mentioning some of the challenges that we face in the RLC implementation. So of course, selecting appropriate reward function was a major challenge. So it is subjective to this system that we are trying to deal with. And the convergence is a major issue in the case of an oral training, unlike the conventional approaches. So it required several simulation trials to ensure that the agent has learned the system dynamics. And finally, tuning the hyperparameter has made the design a little more challenging. So with this, I just would like to thank you and thank Kwanzaa for this opportunity. And if there are any question and answer, I would be happy to answer.
Thank you, Dr. Kumar. That was a great presentation. And as you said, I think we can proceed to our Q&A session. So please, people, this year, you again have the opportunity to interact with us by sending your questions and comments through the meeting chat. Now we've already got a few questions that come in. One of them is in your ILC that you were describing earlier on, I believe for the maglev, the
Yes.
question was, does this take care of both disturbance and noise? If so,
Yes.
how?
Sorry, Mitch, could you repeat the question?
In your ILC control for the maglev,
Yep.
the question is, does it take care of both disturbance and noise, and how?
Yes, it does. Like, I just would like to go to the respective slide and answer. Okay. So we can notice that typically the Q filter, also called a roll-off filter, is chosen to be a low-pass filter because if there is any model uncertainty in the plant, that would be handled through this low-pass filter. And if the system has a tracking error, that tracking error would be filtered out through this learning filter so that if there is any external disturbances, these two filters would handle one for the external disturbance and another one for the model uncertainty.
Okay, great, thanks. Did you use a nonlinear ILC?
No, it's a linear ILC. So it's a linear plant. So here the goal is, of course, the feedback controller could stabilize the plant, and the goal of augmenting this ILC is to ensure that the tracking error is minimized by augmenting this.
Okay, thanks. Now, did you use ILC also for the flexible link compared it to reinforcement learning?
No, we have attempted only deep reinforcement learning controller for flexible link.
Okay,
And currently our team is exploring the possibility of, augmenting this two schemes and trying to identify what are the similarities and differences among these two schemes.
great, thank you. Now, what sampling rate did you use to train your RL agent for the flexible link?
As we want to test it in real time, we use the same sampling rate of say 2 milliseconds. So that I did mention in the parameters table as well.
Now, was that slow when you were doing your training?
Yes, it does. So we had actually used a GPU in order to train the oral. But after initial trials, we were able to ensure that the tracking is significantly better.
Okay, great. Now, why? So you were saying for the really flexible link that you use a closed loop identification technique to
Yes.
build your empirical model.
Yes.
Why did you use that particular technique?
Okay, so as I mentioned, for comparing the performance of this DDPG with its equivalent, conventional approach, that is model predictive control, we need the mathematical model of a system. So for which we went for the empirical model. Particularly, we went for a closed loop identification technique because the RFL is marginally stable in open loop. Again, in closed loop identification, we went for a direct approach. Yeah, so we went for a direct approach so that the kind of feedback controller used is not important. Like whatever be the controller, all we need is only the respective control signals applied and the respective output.
Okay, that's great. Thank you so much, Dr. Kumar. We have one last question, and I think I can answer that from Mr. Padampali Prasad. He asks if Simic used real-time version. Dr. Kumar used our Quark real-time control software, so it was implemented in real time using the Quanser Quark real-time software. So on that note, we are pretty much out of time right now. So again, I'd like to thank you again, Dr. Kumar, for a great presentation. A big thank you to everyone who attended today. And please visit our website at www.quansa.com and our LinkedIn page to find out more about our systems and any upcoming webinars. And on that note, I'd like to wish everybody a great day. Thank you.
Thank you,
Thank you,
Mitch,
Dr. Kumar.
for the
Thank you,
coordination.
Mitch.
Thank you, Gima.
Thank you, everyone.
Thank you, participant. Thank you all. Have a nice day.